Hello everyone. So in today's video we will talk about how to find the solution of a one-dimensional wave equation. So in the previous session we saw how to model this differential equation, and today we are going to find the solution of this differential equation. So the method which we are going to use is a variable separable method. The idea is the same which we did for the solution to one-dimensional heat equation or the diffusion equation. So we are going to apply the same idea over here as well. Okay, so what is the scenario we have? We have a string, and suppose this is 0, this is L. So I have a string of length L. This is my x, this is my u deflection. This x-axis is also called as the equilibrium line. Okay, so now this is always fixed. There is no deflection for this point, and there is no deflection for this point. Only these points will move up and down as my string will move up and down. So here and here there are no deflection, so these points are always fixed at 0. That means what? My boundary conditions will what? So my boundary conditions will be my u of 0 comma t at any time t, and at x equal to 0 my displacement is 0, and at any time t and at the distance L the displacement is also 0. That means at the start and at the end at any given time my displacement will be 0. That means this is always fixed. So these are my boundary conditions. And now what are other initial conditions? Now suppose I give you initial conditions. There will be two initial conditions. So the first thing is there any initial displacement? So the first condition is about the initial displacement. That means what? Initially means when time is 0, u of x comma 0 is something, say f of x. Means what? Initially what I will do is, I will just, so there is a string 0 to L, there is a string, and I am just pulling up this string and leaving it. So it is represented by some function, say f of x. So, and suppose while leaving I apply some force to it. So there are two ways, right? I just simply pull it up and leave it. That means there is no initial velocity. Or another way is I pull it up and then I will apply some velocity as well, so that the movement will be fast. So suppose my initial velocity is also given to me. So initial velocity, which is my u of, means dA by u by dA by t at x comma 0 is some g of x. So this represents what? This is my initial velocity. Rate of change with respect to time is some g of x. So in this way wave equations problems can be categorized into three types. So this I am going to share with you again at the end of the session. But yeah, type 1 we will see that. So these are the possibility, right? Either we give only initial displacement, we do not give initial velocity. We don't have initial displacement but we give some initial velocity, and we give initial displacement also and we give velocity as well. So these are the three categories a wave equation can be classified as. Both 0 is not possible, right? Initial displacement is also 0 and initial velocity is also 0. That case is not possible, right? Because if both the things are 0, that means what? There is no wiggle. It's only the string is in the equilibrium position. That means there is no wiggle of the string, so there is no deflection. So both 0 is not possible. So either both will be non-zero, or this 0, this non-zero, and this 0 and this non-zero. So I will give three different formulas for all the three scenarios. So first let's do some basic building blocks for this derivation. So we go the same way, we go by variable separable method. So what does the variable separable method say? So let u of x comma t, which is my solution, so it can be written as product of function of x and the function of time. And since it's a solution, it will satisfy the differential equation. So my uxx will be nothing but x dot dot into t, and my utt will be nothing but x into t dot dot. So when we put them in our wave equations, what is our wave equation? DA bar square, this is minus 2, into dA bar square u upon dA bar t square. So when I put them over here, what I get? X double dot into t equal to c raised to minus 2 x t double dot. And if I take all variables on one side, what I get is t double dot upon c square into t. So now again the same argument which we gave for the heat equation derivation. So this is a function of x, this is a function of t, and I'm saying both are equal. That means it has to be some constant k. And if I solve them one by one, I get x double dot upon x equal to k, and I get t double dot upon c square t equal to k. So therefore I have x double dot minus kx equal to 0 and t double dot minus c square k into t equal to 0. And now we will solve these two equations one by one. Now let's use our boundary conditions. So what was our boundary conditions? My starting and end point, they don't show any deflection. That means they are at the 0 position at any given time t. So if I use this thing, so what is 0 is equal to, so let's use the boundary condition. So what is my u of 0 comma t? U of 0 comma t is nothing but x of 0 into t of t. So this same, so product is 0 means one of them has to be 0. But if this is 0, that means my u will be 0 and I will get a trivial solution. But I want a non-trivial solution. That means this is non-zero. Therefore I have x of 0 equal to 0. Same scenario, 0 is equal to u of l comma t is equal to x of l into t of t. And this implies what? Again the product is 0. So one of them has to be 0. But this is non-zero. So therefore my x of l equal to 0. So x of 0 and x of l are coming out to be 0. Okay, so now let's again come back to this equation. So let's solve this first equation. So now what is this? My k is what? Any real number. So my k can be either greater than 0, it will be less than 0, or it will be equal to 0. And now we will see that k greater than 0 and k equal to 0. These two cases are not possible. Why? Because if k is greater equal 0, then we will always get the trivial solution. So let's try to convince ourselves with this case, means these two cases first. So now suppose my k is 0. So suppose my k is 0. So what do I get? I get x double dot equal to 0. So what is my x of x? Is some ax plus b, where a and b are constants. And now yes, let's use the previous thing. So let's use the previous thing. So previous thing as in, we have that x of 0 is 0, we have x of l is 0. Now if I use these two conditions over here, so what is given to me? 0 is equal to x of 0. But what is x of 0? It is a into 0 plus b. So this implies my b is 0. And x of l equal to 0 means what? A into l plus b. So this implies 0 is equal to a into l, my b is 0. So 0 is equal to a into l. But my l is non-zero because I have a string of length l. So if my l is non-zero, therefore a has to be 0. So my a is 0, b is 0. Therefore my x of x is what? It's 0. But if my x is 0, that means what? My u also becomes 0. My u also becomes 0. But again, which is not possible because we want a non-trivial solution. So k equal to 0 is not possible. Second case, this was my first case. Second case, suppose my k is strictly greater than 0. So let's call k equal to some lambda square, where lambda is also positive. You can always write a positive real number as a square of a real number. Okay, so when this is the scenario, what do we have? We have x double dot minus lambda square x equal to 0. So this is nothing but my second order linear differential equation, ordinary differential equations. So if you find this auxiliary equation, r square minus lambda square equal to 0, so r is what? Plus minus lambda. Therefore your x of x, since the roots are real and distinct, therefore you have, it is a into e raised to lambda x plus b into e raised to minus lambda x. Okay, now let's again jump to our boundary conditions. Let's use these boundary conditions once again. So what do I get? I get 0 is equal to x of 0 is equal to a plus b, because e raised to 0 is 1. So I have a equal to minus b. And what another thing I have? 0 equal to x of l, a e raised to lambda l plus b e raised to minus lambda l. But what is my b? B is minus a. So if I take out a outside, e raised to lambda l minus e raised to minus lambda l, because my b is nothing but minus a. But if you recall some identities involving exponential and hyperbolic functions, if you recall, your cos theta is nothing but e raised to theta plus e raised to minus theta by 2 cos, and your sin hyperbolic theta is e raised to theta minus e raised to minus theta upon 2. So here we are having minus. So what is this? This is nothing but if I use this formula, so I have 0 is equal to a into sine hyperbolic of, what is my theta over here? My theta is lambda L 2 times. So this is what I have. So the product is 0, so therefore either a is 0 or sine hyperbolic of lambda L is 0. But there is a result that sine hyperbolic theta is 0 if and only if my theta is 0. So if this is 0, that means my lambda L is 0. But my lambda is strictly positive and my L, which is the length of the string, is also positive. You have a string of non-zero length. So therefore, since both are positive, so product can't be 0. So this case is not possible. So this implies my A is 0. But what is my B? My B is nothing but minus A. So if my A is 0, this implies what? Our B is also 0, and therefore my X is again identically 0. And again I get a trivial solution. So again my K greater than 0 is not possible. So K equal to 0, K greater than 0, both cases are not possible. So let's go for the third and the final case, which says suppose your K is less than 0, that means your K can be written as minus of lambda square, where lambda is a positive real number. Okay, if I do this thing, then what do I have? I have x double dot plus lambda square x equal to 0. Again auxiliary equation will imply r square plus lambda square equal to 0. So your r is what? Plus minus lambda I. And therefore what do you have? You have your x of x is equal to, it is nothing but a cos of lambda x plus b sine of lambda x. So this is what we are left with. And now let's try to find our a and b. Let's use the same boundary conditions. So 0 is equal to x of 0 is equal to a cos 0 is 1, sine 0 is 0. So this implies what? My a is 0. And 0 is equal to x of L. So that means what? I have a is 0. So I have b sine of lambda L. So now again the product is 0. So either b is 0 or sine of lambda L is 0. But again if I take b equal to 0, my a is 0, b is 0, I again get a trivial solution. My x will be 0, hence my u will be 0. So you assume that your b is non-zero. So this implies what? Your sine of lambda L is 0. But when sine theta is 0, if and only if your theta is what? It is an integral multiple of pi. So what is your lambda? Your lambda is nothing but n pi upon L. So whenever your lambda is n pi upon L, my this product will be 0. So therefore what do I have? If I take b to be 1 for simplicity, I get x of x equal to sine of lambda is what? N. So n pi x upon L. And as I keep on changing n, I get different lambdas. So let me call this as xn of x. That means I am getting different solutions. So that is one thing. Okay, now let's try to solve the problem for, here my n is what? 1, 2, 3 and so on. Now let's do the same thing for my t double dot, because I have one more equation, right? So if I do the same thing for t double dot, what do I have? I have t double dot minus c square. What is my k now? Lambda square t equal to 0. So from here what is our auxiliary equation? R square equal to minus c square lambda square. So r is nothing but c lambda I plus minus. So this is what my roots are of the auxiliary equation, and therefore again your solution becomes t of t is nothing but a cos of c lambda t plus b sine of c lambda t. Okay, so this is what we have. And now here I don't have any boundary conditions for t of t, right? I had boundary conditions for x of 0 and I had this u of 0 t and u of l comma t, and because of which I got x of 0 was 0 and x of l was 0. But for t I don't have any conditions, but then yes I have some lambda. So what are my lambdas? My lambdas are nothing but n pi l upon l. So my t of t is nothing but, I will write again n, it is a n cos of lambda n ct plus b n sine of lambda, because my lambda n's I found in my previous case as in this part over here. These are my lambdas, and therefore what is my solution now? So what is my un of x comma t? It is nothing but xn of x into tn of t. And if I take the product, so what is the product? Product is nothing but, what is xn of x? Xn of x was nothing but sine. It was sine of n pi x upon L into an cos of n pi ct upon L plus bn sine of n pi ct upon L. So this is what my un. You take u1, u2, u3, u4, you have infinitely many solutions. And again, if I use the superposition principle of the linearity principle, let me call u of xt is equal to summation un of x comma t, where n is running from 1 to infinity. Since again our wave equation is a linear and a homogeneous partial differential equation, so addition of two solution will again be a solution. And if I add infinitely many solutions, in this case, because we are in a very nice world, this also forms a solution and they satisfy the boundary conditions. So what is my solution finally? So finally my u of x t is nothing but, my u of x comma t is nothing but summation n runs from 1 to infinity an cos of lambda n ct plus bn sine of lambda n ct, and you whole multiply it by sine of lambda n x. Now the question arises, what are my ans and bns? Okay, so now for that let's come to our initial conditions, that means our initial displacement and the initial velocity. So now suppose your initial displacement is f of x and initial velocity is g of x. Now we will use these two conditions to find our ans and bns. Okay, so let's go one by one. Suppose your initial displacement is f of x. So now what is given to me? U of x comma 0 is nothing but f of x. So if I put this over here, my f of x is what? It is summation n running from 1 to infinity. My t is 0, so this becomes 1, this becomes 0. So it is nothing but an sine of n pi x upon L. Because cos becomes 1, sine goes away, so we are only left with an. And what is this? Again, if you come back to our Fourier series, you can see my lectures on Fourier series. There we have done half range expansions. So what are these ans? They are nothing but, they are the Fourier coefficients. They are the Fourier coefficients in the half range Fourier sine expansion for the interval 0, L. So if I take this, then they are the Fourier coefficients. And whenever we have such a scenario, since we have sine terms, that means it's an odd extension, and your ans are nothing but 2 upon L integration 0 to L f of x into sine of n pi x upon L dx. So this is what my ans are. So once I have my initial displacement, I can find my ans using this formula. Again, to make sure this integration exists, our function should be what? It should be piecewise continuous function. The representation of Fourier series, we saw that in the lecture, that you can see the link in the description for that lecture. So my function should be piecewise continuous function, and because of which I can find integration exists and I can find an, and when I put this ans over here, this series is actually equal to the given function. So this convergence is a nice convergence. Okay, now let's try to find our bns. To find bns, we will use our initial velocity. So what is given to me? Del by u by del by t at x comma 0 is nothing but g of x. So what is del by u by del by t? So if I differentiate this, my del by u by del by t is nothing but summation n from 1 to infinity. It is minus lambda n an sine of lambda n ct plus bn lambda n c cos of lambda n ct. This is sine of lambda n x. So what is this at? This is g of x at x comma 0. So this goes away. So what I am left with, summation n from 1 to infinity. It is nothing but bn into lambda n into c into sine of n pi x upon L. So this is what I'm left with, because this is a differentiation. When I take at x comma 0, when I put t equal to 0, this term goes away. Cos of 0 is 1. So bn lambda nc, bn lambda nc, and sine of n pi x upon L. And again the same thing, right? What is my g of x? It is nothing but the, so what is this coefficient? It is nothing but the Fourier coefficient, right? Half range Fourier coefficient. So in that case, my bn into lambda c is nothing but, so therefore my bn into lambda n into c is nothing but same thing, 2 upon L integration 0 to L g of x sine of n pi x upon L dx. So what are my bn's? My bn's are nothing but 2 upon, what is lambda L? It is n pi upon L. So it is nothing but over here n pi c, L and L will go away, integration 0 to L g of x sine of n pi x upon L dx. So once I know the initial velocity, I can find my bn's, and to find an's we will need initial displacement. So this is the formula for your wave equation, and that's how now we can summarize our solutions into these three categories. So boundary conditions will always be fixed. Initial, suppose the displacement is given to you and initial velocity is not given to you. That means what, your g is 0. In such a scenario, since initial velocity is 0, that means what, your g is 0, that means what, your bn's will be 0. So for type 1 scenario, that means when only initial displacement is given to you but initial velocity is 0, in such a scenario your type 1, okay, let me write here on the new page. So in case of type 1, what is my type 1? When my initial displacement is given but initial velocity is 0. So that means since my g is 0, my bn's becomes 0, and therefore what is my u? My u of x comma t is nothing but summation n runs from 1 to infinity an cos of n pi ct upon L into sine of n pi x upon L. So this is the formula. Yes, I think it's not visible. Yeah, so this is the formula when my initial velocity is 0, because since my g is 0, my bn's becomes 0. So this is what my formula is. An is the same thing which we just derived. For type 2, that means what, my fx is 0. That means what, initial displacement is 0 but there is some velocity. So in such a scenario, what, my f is 0, and since my f is 0, my an will become 0. So what I get my solution will be of this form, summation n running from 1 to infinity bn sine of n pi ct upon L into sine of n pi x upon L, and where bn is given by the previous formula. So whenever your initial displacement is 0, your solution will involve both sine terms, and when initial velocity is 0, your solution will involve cos and sine terms. And what was the third case? Third case is when both are non-zero. When both are non-zero, your u of xt is nothing but summation n from 1 to infinity an bn, and this is sine. Because your both are non-zero, so this is an cos of n pi ct upon L plus bn sine of n pi ct upon L. So whenever in a question you just see which one is 0. If both are non-zero, then both cosine and sine term will be there for the parameter t. When initial displacement is 0, then only sine terms, and when initial velocity is 0, cos and sine terms will be there. So this is what you are supposed to take from this lecture. Whenever you see a question, see which part is 0 and accordingly use the formula. So I hope this part is clear. If you have any concerns, you can ask me in the comment section. Thank you.